That worked. Thanks. Welcome, everybody. Actually, welcome to approximately the halfway point, maybe a little past the halfway point in the summit. So congratulations, you made it. So good job, round of applause. Wanted to just spend a bit of time today talking about modularity, specifically around the fact that with this Gen AI revolution, there's been a lot of really fast movement. So things are moving fast, which means we're kind of moving in a couple of different directions. So I'm trying to put a bit of a pause on that just to see if we can maybe try to think around how to kind of go back to a little more standardization. So what I wanted to do today is really cover three main things. If this thing will let me click, there we go. The first kind of challenge that we're seeing is just the incredible pace the innovations are happening, both at the GPU level, the CPU level, and the network to follow. But we're seeing really a difference in speed at which things are innovating. And so we're starting to see disconnects between the GPUs, the CPUs, and the NICs, and that's forming kind of a problem where we're having to build platforms that are mixing, for example, PCIe generations in order to kind of keep everything running. So that's a big challenge. The other one is actually the fact that as we scale these big GPU clusters, we're actually noticing that there is this bigger need for higher reliability. And the main problem is the bigger the cluster, single failures, like a single GPU failure, can actually cause those clusters to kind of pause and have to restart. And so that problem isn't going away. It's actually getting worse as we move into these bigger clusters. The last piece is really around the kind of evolving ecosystem as we start developing these AI platforms. Not sure how many people in the audience here are currently building AI hardware, but you can only imagine we used to see fairly common platforms, fairly common ratios between GPUs, CPUs. That's the reason OCP released the OAM spec, and it's been excellent for us. It's scaling quite nicely, but it's starting to change, and we are starting to see changes there that we need to be somewhat dynamic to. So I want to focus first on the problems, and then I'll kind of go through. I think I got a note about turning off notifications. Sorry about that. So the first one really is, how do we deal with this ecosystem where we've got, in the past, everything was kind of matched, right? We followed a very standard kind of timeline. Everything kind of got to different PCIe generations at the same time. It meant that 400 gig NICs could then be bandwidth matched to your GPU in PCIe Gen 5 in this example. So nicely matched, everything works. We kind of just proceeded along a 2.5 year cadence. So what's happening now is really GPUs are starting to move a little faster. They need to innovate. They need to get more HBM. They want to scale. And so their ingest bandwidth is actually increasing pretty drastically, right? So they've gone to Gen 6, so they've doubled their ingest bandwidth. The NICs are still at 400, so now we've got a little bit of a bandwidth mismatch, which results in this kind of underutilization, right? We're unable to feed the GPU with all the data that it could actually consume. And that is doubly worse for both inference and for training. So the next problem that comes up is this kind of reliability piece. And I wanted to bring up, I think maybe many of you have read this paper, but there was a paper published by Meta in 24. They had this big Llama 3 model, 405 billion parameters. They ran it for 54 days. And in that 54-day period, let's ignore the problems we can't necessarily solve. So of course there were problems related to GPU, but I wanted to highlight these two here. So network switch or cable. So switch dies, cable gets unplugged, something gets bumped. 8.4% of their failures were due to that, and then 1.7% on the NIC. So that's a total of about 10% of all of the kind of interruptions that occurred in this training run. Now, an interruption has variable meaning. In most cases, this training platform has to pause, it has to go back, it has to pull checkpoint data, and then it has to restart. So when you look at the total number, over a 54-day period, it was interrupted 42 times. So that's almost once a day. So once a day, this thing had to pause, go back to checkpoint, and restart. And this problem is only going to get worse because these models are getting bigger. We're actually going to get more network, more GPUs, more scale out. So what's kind of interesting is the reason for that is that these kind of TensorFlow style parallelism that happens from these models and the model training, they're running all of these GPUs in a sort of massively parallel fashion, and they require all the GPUs to kind of pull their weight. And so if there is an interruption to kind of a GPU, it actually impacts not only the one GPU, but it impacts the cluster, because they kind of have to wait, right? This one GPU has lost its network connection. We've got this one NIC. It can't get data, so it pauses. Now they got to go restart. So number 3, what else is up there? We have this sort of traditional host interface board kind of platform in front of us. This host interface board is well matched to our UBB that we've been running for a long time, which is great. But unfortunately, the shape of these things continues to change, and you've seen, recent announcements. There's these 2 GPU, 1 CPU systems. We've seen 4 GPU, 1 CPU systems. We see 4 GPUs, we see 6 GPUs. Of course, we still see 8 GPUs. We see everything in between. And so the problem is the scale up in the back is changing quite drastically. And not only that, it's changing rapidly. So it's really hard to build a system that helps kind of adapt to all of those pieces. And that makes it really hard for it to adapt to changes in the future. So as we move to different inference applications, as we move to different training applications, it just makes it a little harder to scale because we don't really know what that back end's going to look like. So on top of that, this is all changing very quickly, and that's just because that's the nature of the game right now. So I believe that we do need some way to be able to be a little more flexible and modular to this, because it's going to be very difficult to keep up as you continue building platforms. You probably don't want to be building 9 different host interface boards to support these applications. So there is a little bit of light at the end of the tunnel. There's some kind of solving one problem actually ends up solving another. And so, of course, the one potential easy way you could solve this is you just simply match your network bandwidth, right? So just add another NIC. And what that does is it doubles the bandwidth. You keep your NICs at Gen 5 until you can wait, right, until the Gen 6s are available. You double that up, and then you get your bandwidth match. So that's sort of your step 1. But there's actually this extra benefit, which is you kind of double up your network. What that actually means is you actually have a backup path if you have a failure. And that makes you a little more resilient to your NIC issue, and your GPU actually doesn't necessarily stop. It actually kind of reduces its ingest bandwidth. So it runs a little slower, but it doesn't require a full cluster restart. And then lastly, if we can just wrap up that whole kind of solution into something that's a little more modular, you end up with something that actually matches quite nicely. It kind of aligns to your kind of your GPU, right? So instead of creating these larger host interface boards, maybe you create a lot of smaller boards and they match up to your GPU so that you can be a little more flexible. In this example, I have a 400 gig NIC option, as well as a 2 by 400 gig option, depending on what ratio you want to use for your network. But this type of board then allows you to kind of create this like atomic unit, right? For every GPU in the system for these kind of applications, they have a dedicated ingest path and a dedicated scale out path in order to provide data in and out of that GPU. And it scales because it is atomic. So some extra benefits that happen if you do this, well, there's obviously the ability to scale, but there's also, you can build these pretty quickly. It's a board, it's small, you can perhaps cable it in. Gives you a little bit better signal integrity because maybe the devices are a bit smaller. They break out a little more cleanly. You reduce your crosstalk. You end up with better signal integrity. You end up with better reliability. Gives you the bandwidth matching and redundancy that we just mentioned. And it allows you to kind of apply it to any shape, really. Doesn't really matter how many GPUs they place in the back, right? It's fully open. So as a quick call to action, we talked a lot about the fact that these models for AI training and inference, they're kind of forcing a lot of different shapes. And that's resulting in not just the number of GPUs changing in the back, but actually this differentiation in PCIe rates. We're getting mixtures of Gen 5 and Gen 6. And that's going to continue to widen. So we need to kind of be able to address that. And then, of course, at the same time, with these clusters getting really big, we're going to need to figure out how to kind of increase reliability. So one of the things I'm suggesting is really, take a look at these problems. Maybe there are some opportunities to turn a problem into a solution, and maybe that solution can actually solve a few different problems. This is just one example, but really reducing your design into something that can scale may provide a lot more flexibility, and then you get kind of redundancy as a benefit. And yeah, please do visit us in the Astera booth in B13. We also have kind of an example of what these modular boards might look like. That's in the OCP Innovation Village, just kind of in the back in the main show floor. So we'd love to have you guys come by and ask us questions. Thank you.
Yeah, we have time for a couple questions.
Thank you so much for your talk. My question is, you talked about CPUs, GPUs, and NIC, but have you guys considered other type of accelerators that are coming up? I mean, not only AI, but for scientific applications and other things. How that get into the mix of all the complexity?
Yeah, that's a great question, and that's really my fault. When I usually refer to GPUs, I'm kind of including pretty much any accelerator that scales. So the problem statement stays the same as long as the accelerator has similar requirements in terms of getting data in and out of the unit itself. So it does apply. It really depends on the application. For an accelerator for scientific operations, if it has data ingestion challenges, then this type of modularity would work for them as well. No problem. Any other questions? All right, thank you so much.
Thank you, Wesley.